Okay? Okay, so we were talking about the details of class diagrams in Chapter 5, and we got to the point where we were talking about various issues to do with generalizations, and we're just going to recap for a few seconds. If you remember on slide 18, we talked about the generalization triangles, which we've seen before, pointing up to the superclass, and you can add these discriminators. And then on slide 19, we see a situation where we have cases where you have unnecessary generalizations. In particular, we have subclasses of audio recording, which, like jazz, classical, blues, rock, etc., where you don't really want to have all of those classes, because that means that if you ever create any new types of music in your system, you're going to have to create new classes, which means more programming. Okay, what you want is you want to be able to change the data, not the programming, when you add new categories. And so the class diagram in the middle, where you see recording category, shows that what you can do is add a single class called recording category, and then add new instances of that class whenever you want to add new types of music. Now this kind of transformation between a class hierarchy and an instance, or a set of instances, only makes sense when the classes are not going to have different attributes. And we can see that in the hierarchy at the top, basically all audio recordings are going to have the same attributes. They're going to have, you know, the type of music, the artist, the length of the recording, various kinds of things. But they're not fundamentally going to have different attributes, whether it's jazz, classical, blues, or rock. Okay? Unless you really get down into picky details that most applications wouldn't need. And so in general, when you do have the same attribute belonging to all of the classes, that's another reason for not having a whole bunch of subclasses. Okay? So if we could just have one or two attributes that are common to all audio recordings, we just need the audio recording class, or, as we said, better yet, create a recording category class that has the attributes like description and artist and length and things like that. And actually, that would be the recording. Sorry, the recording class has the title, the artist, the length. The recording category has the description of the category. Okay, so much better way of dealing with things than having all kinds of unnecessary classes in a hierarchy. Any questions about that? At the bottom, we see the instance diagram. In fact, you can see the same old hierarchy with recordings, audio recording. So here we see audio and jazz, classical, blues, and rock. Down the bottom you see as an attribute value, jazz, classical, blues, and rock. Okay? And you can also see how we can extend that hierarchy still further. So we have the Ninth Symphony by Beethoven as a kind of classical, and Let It Be by the Beatles as a kind of rock. But actually, we're not extending the hierarchy. These are actual recordings. Sorry, these are instances of the recording class as opposed to instances of the recording category class. Okay, so we could extend the hierarchy further. We could break down classical into, you know, Baroque and 20th century classical and so on if we wanted to. But we can also tag our recordings directly onto any of the existing categories or any of the subcategories. Question?
Why do you have a colon in front of each name?
Every instance, the colon there is to distinguish that it is an instance, not a class. Okay, so these are not classes, these are instances, and you must have a colon, you must underline it. Okay, so that's why we do that, and that's how you can visually tell whether it's an instance or a class. Any other questions? All right. Now, one of the things that we said is that you can have a number of different ways of breaking down a superclass into subclasses. So we said we can break down animals based on their type of food or based on their habitat. And one strategy, if you do have multiple ways of breaking down a class into various detailed types of subclasses, is to say, okay, first of all, we're going to break it down by habitat. So animal breaks down into aquatic and land. And then, in order to have the breakdown by type of food, each of those can then be broken down by type of food into carnivore and herbivore. So aquatic carnivore, aquatic herbivore, land carnivore, land herbivore. Okay, that's a strategy if you really did need to have those distinguishing features. So now we have 4 classes at the bottom and 3 classes up above. Okay, so in fact it's a little binary tree. Quite a lot of classes here just for this kind of breakdown. Can anybody tell me any drawbacks, any problems with this hierarchy as it stands? I don't like this hierarchy, so can somebody tell me what's wrong with it? Yeah?
There's some parts that are redundant between classes like carnivore, herbivore, vegetable.
Okay, there's redundancy. To be more precise, we're going to have information to do with being a carnivore in aquatic carnivore, and the same information in land carnivore, and information about being a herbivore here, and the same information there. So attributes are going to have to be put in 2 different places. We're not inheriting from a superclass, which is what we really want to do. But we can't do that because the only common superclass is animal, and we wouldn't want to put all the carnivore information plus all the herbivore information up here. The attributes wouldn't belong there. Anything else wrong with this? Yeah?
We can have animals that are carnivores and herbivores.
Right, okay. Right now we can't have animals that are carnivores and herbivores at the same time. So we could add omnivorous, aquatic omnivore and land omnivore. We could do that, but then we're going to have to get even more duplication, right? We're going to have in the omnivores, we're going to have the type of hunting strategy they use in both of the carnivore classes and now both of the omnivore classes, and the type of vegetation they eat in both of the herbivore classes and both of the omnivore classes, and so it gets really messy. Okay, so that is a problem with this hierarchy because of this. There are several any other problems? Yeah?
It doesn't account for amphibious animals.
For what animals?
Animals that live in the water and land.
Oh, it doesn't. Oh, yes, right. It doesn't account for amphibious animals either. Right. Okay, good point. Okay, so we're going to add now amphibious, omnivore, carnivore, and herbivore. Right? So hey, how many classes are we going to have in our system eventually? Like just an unbelievable number. So when you start seeing this kind of thing, you begin to realize that you've got to use some different strategies. So one strategy is to make a huge mess like this on slide number 21, and to use multiple inheritance. Now this doesn't work in Java though, so that's an immediate thing that we have to think about. But if we're programming in C++, you can do things like this. So here we've got aquatic carnivore, subclass of both aquatic animal, and if we can follow these little bumpy things along, carnivore. Okay? Okay, it's messy, and this kind of messy diagram is prone to bugs, and yeah, we've still got to add the omnivorous ones, and we can do that. We can have, subclassing off both carnivore and herbivore, and the ones which are both aquatic and land, the amphibious ones, so we can actually have something that's a subclass of all 4 of these things, and an amphibious omnivore. We could do that, but it's beginning to look a little bit silly. We will see in Chapter 6 a much better solution to this called the player role pattern. Okay, so we're going to defer some of the discussion of this until Chapter 6. The lesson I want to give you now is be careful of generalization. Don't just use generalization whenever you think it might be reasonable. Okay, the Chapter 6 will get into the solution to this problem, but be aware of it at this point. Another thing we have to watch out for in generalization is a situation where you have an instance that is of some class, and that instance represents something in the real world that at some point in time changes class, or changes what it is in the real world. For example, if you register as a full-time student, and the system has an instance of full-time student representing you, you might decide at some point to go part-time, right? Well, that's not a good thing from the system's perspective, because now the system has got to delete the full-time student object and create a part-time student object. And we don't really want to do that, because that requires an awful lot of programming work. If this is stored in a database, we've got to delete the record and add a new one. Maybe we can change an attribute, but in object-oriented databases, that's not the way you do those kinds of things. If it's in memory, we've got all kinds of pointers pointing to these things. to you as a full-time student. Your object is a full-time student. We've got to make sure those pointers are re-established to the new object. In general, programming languages don't allow you to change the class of an object. There are some programming languages that do. Okay? Smalltalk, in fact, does have a mechanism that allows you to change the class of an object, but it causes all kinds of bugs in and of its own right. All of a sudden, an object is of one class and it changes to another class, and it's in a variable which may be not compatible with that new class, right? The variable's type, you know, and the method you're going to send to that variable will now no longer match the class of the object. And so, generally speaking, they design programming languages so you can't change the class of an object. What that means, bottom line, is don't create hierarchies where you're likely or typically normally going to have to change the class of an object. So this kind of hierarchy with full-time student, part-time student is not good. We probably want to stick with just student and use attributes to say if it's full-time or part-time. Okay? You might say, well, there's going to be different methods for full-time and part-time. The fees are going to be calculated differently or things like that. Well, maybe so. In which case, we're going to use other strategies to deal with that. Again, we'll see the strategies for that in Chapter 6 when we get into the patterns. But just think about, don't have don't have too many types of subclasses, because you might get into big messes like this, or big messes like the multiple inheritance mess on the previous slide. We've seen instance diagrams. We saw one a short while ago and a couple of slides back. We also saw one quite earlier on in the course, in Chapter 2. And I told you that the key is they have a colon in them. Preceding the colon, optionally, the name, the description, the key attribute of the class. In this case, there's an attribute maybe called name for employees. So we actually put the data for name. And we can also have the class name after the colon. Either one is optional, but you've got to have both. You just put whichever one conveys the information you want to convey. And you have to underline it as well to make it visually clear that it is an instance. Remember that on instance diagrams, you never have any multiplicity because the multiplicity is always one-to-one. Okay, this object is connected to the Pat employee object is connected to the company object by a line which says that there is a connection at runtime. There is some kind of a pointer or reference between these two, and that represents, it's effectively an instance of the association is employed by. Okay, so these things which are instances of associations are called links. That's the UML terminology for the links, or for the lines in instance diagrams, so don't confuse them with associations. An association is an abstraction of a set of links. Okay, a link is a single pointer between objects. An association represents the potential set of links that can be between objects of one class and objects of another. Okay? Very important to understand that distinction. One of the things that I might ask you to do in a test is to say, given an instance diagram like this, tell me what the class diagram is. Okay? So, what is the class diagram that this picture on slide 23 represents? Can somebody tell me what are the classes involved? Once you understand the diagram, it's a very trivial problem. What are the three classes involved?
Employee, company, and board.
Right, okay. So first thing is just look at the names of classes. There's only three there, right? Employee, it's all these ones, company, and board, okay? It looks trivial, right? But you'd be surprised how many people on a test don't notice that. Secondly, what are the associations?
Many.
Yep.
Many employees for one company.
Okay, we've got more than one employee to a company here, so there's at least a many. An asterisk will go on the employee side of this association. And company, probably one. We don't have any examples of more than one here, so one would be a reasonable assumption. Although conceivably there could be, just no examples shown of more than one company, but it does certainly seem like many to one. And
company to board.
Company to board.
1 to 1.
Seems like 1 to 1. Okay, we don't have any contrary cases to that. Yeah. Question.
For employee and company, the colon comes before the class. Nothing for board. For both of them, they don't come
before the class?
That's because we don't have the class name shown. The class is, I'm illustrating that you can leave the class name out if you want. It just depends on what information you want to convey. Okay. And that's a very good question, though. You know, it's an astute observation that we don't have, you know, the colon comes at the end, but that's just because the class is missing. Any other questions? Okay. Make sure in your minds you have a thorough understanding that associations and generalizations are fundamentally different. Okay? An association is quite different in nature from a generalization. A generalization is describing the relationship between classes. An association is describing the potential relationships between instances. Okay? And a generalization never exists between instances. There's no such thing as like a link of a generalization. Okay? Generalizations only ever exist between classes. When you turn a class diagram into, and you generate an instance diagram from it, all traces of the generalization vanish. All you're left with is instances of the concrete classes. You never have instances of any superclasses unless they're concrete. But even if you do, then they don't have any trace of their subclasses. Okay, so you only have a few concrete classes connected to each other. Okay, so all traces of generalization vanish in instance diagrams. Whereas with associations, you get links in the instance diagrams. So let's look in detail at what these two paragraphs or bullet points on slide 24 are saying. Okay, associations describe relationships that will exist between instances at runtime. Okay, so there will be instances of both classes joined by an association once in the instance diagram. Generalizations describe relationships between classes strictly in class diagrams, okay, and as we said, they don't appear in instance diagrams at all. And the last point is key. An instance of any class is logically considered an instance of its class plus instances of it, plus also an instance at the same time of its superclasses. So if I've got shape 2D, subclass, arbitrary shape, subclass, let's say, I forget what the hierarchy looked like. Anyway, shape 2D at the top and rectilinear shape in the middle and rectangle at the bottom. Okay? Well, if I have an instance of rectangle, that is also at the same time an instance of rectilinear shape, and also at the same time an instance of shape 2D. Okay? Because it inherits all those things, and the generalization collapses into the instance. Does that make sense? Very important to get that concept. The generalization does not exist on instance diagrams. It's all collapsed into the instances. Right? Good. That may seem like an academic point, but when you're doing analysis and drawing these diagrams and thinking about systems, if you don't really deeply understand that, you're going to lead you to make mistakes. So make sure you deeply understand it. Aggregation. Another kind of thing that you can see on class diagrams. Aggregation is a special kind of association. It is an association. Okay? It's just an association with a little bit of extra meaning behind it that is important, and therefore we give it a special symbol. But fundamentally, aggregations are associations. They represent part-whole relationships. Relationships where you have some object that is logically broken down into parts. Okay? So a car is broken down into parts. A country is broken down into regions, which are logically parts. Okay? A building is broken down into rooms, which are logically parts. The diamond is the symbol that we draw to represent the whole. Okay, so vehicle is the whole, vehicle part is the part, so the diamond goes pointing to the whole, and country breaks down into regions, same concept. The whole side is sometimes called the aggregate or the assembly, and the part side, well, it's just the part. Okay? Okay, and we don't have to put a label on the association if we don't want, because the default under these circumstances will be is part of. So vehicle part is part of vehicle. Region is part of country. Okay. Ordinary association, we can say hazard if there's nothing else telling us what to do. With an aggregation, we can say is part of. These act like ordinary associations. They can have multiplicity on both ends. So a vehicle has many parts, but a vehicle part can only be part of one vehicle. A country has many regions. A region is part of only one country. Typically, it's one to many, whole to part. There can be certain circumstances where a part can be at the same time a part of two things. That's less common. Can happen. You can have multiplicity on the whole end. Much less common, as I said. Okay, so we have this diamond, and notice it's an open diamond by default, it's not filled in black. There is also, in a coming slide, a thing called composition, but we'll get to that in a second. So when do you use aggregation? Slide 26. You use aggregation only when there really is a real part-whole relationship. There's a tendency for people to overuse it. There's a tendency for people to say, gee, I have an association, I'm going to put an aggregation symbol on there. And sometimes people literally put aggregation symbols on every association because they don't really understand the concept properly. Okay? So if you can say the parts are part of the aggregate, or the aggregate is composed of the parts, so a country is composed of regions, you know, that in English, then it's reasonable to use aggregation. Okay? My suggestion also is to look at this question. When something owns or controls the aggregate, then they also own or control the parts. Okay? To some extent. So if I own, you know, if I'm the Prime Minister of Canada, or the people who live in Canada, I'm also the Prime Minister of the people who live in the provinces of Canada. You know, that's the kind of concept. Okay, there is some kind of it's not inheritance, but there is some kind of a relationship between owning the aggregate or controlling the aggregate that also ripples down to the parts as well. If I own a car, I own its parts. Okay, that's a clearer relationship. Okay, so think about these things before you put aggregation on there. And if in doubt, leave aggregation out. Okay, you do not have to put the aggregation symbol. It is not wrong to leave the aggregation symbol out there in the sense that it leads to the wrong decision making. The aggregation symbol gives extra information. So if in doubt, leave it out, because all you're doing is leaving out extra information. And in UML, that's perfectly valid to leave out extra information. Okay? If you need to convey the information for design reasons, by all means, put it in. But only put it in if you're confident it really belongs. Any questions about aggregation? Okay. Composition is a special kind of aggregation. Composition is a stronger aggregation. It effectively says, if we have a composite and we destroy it, then we also destroy the parts. Okay? So if I have a building and I destroy the building, the rooms that exist in the building cannot continue to exist, like floating in thin air up there, you know, high up in the building. Right? You know, if you demolish the building, you're demolishing the rooms. I mean, inevitably. Right? So this is an example where composition would be reasonable. There are other situations where composition may or may not be reasonable depending on the application. So for example, I'm showing down here employee having an address. Okay, I might say that I am going to make sure in my system that if I just delete an employee from my records, there's no point keeping around that employee's address, so I'm going to delete it. Okay, it's just pointless having a floating address loose out there that has no purpose. So by using composition, what I'm saying is I'm giving my designers the capability of, in fact, in some sense, merging. And in C++, I can actually do this. I can actually put the address object right inside the same memory as the employee. And that would typically be done in a language like C++. Okay? In Java, I can't do that. In Java, the implementation is just like any other association. But I have to have code that says that when I destroy the the aggregate or the composition class, I'm also going to destroy the parts. Okay. So it requires a bit of extra programming. Yeah.
There's two different ways of looking at it. For example, a building is made up of rooms, right?
Right.
So if you destroy the building, obviously you're destroying the rooms at the same time. So it's not, the rooms are not being affected, but let's just say you have a class where there's smaller classes that are attached to it, that are not making up the main class.
Right. Okay.
Would you still use?
Her question is what if I had smaller rooms or annexes attached to the side of a building, which are, well, the concept there is they're not parts, right? If they're separate things, they're not parts. Okay.
They rely on the.
If they rely on, well, okay. Now you're getting into a situation where I have smaller buildings that rely on the existence of the larger building. Well, I wouldn't use aggregation under those circumstances. I only use aggregation when I'm sure it's real part, and I only use composition when I'm sure that it's a real part that has to be destroyed when the whole is destroyed. Okay? Yeah.
How about employee and company? Can we consider them as an aggregation, like employees?
Company and employee. Okay, that's it. Okay, he has an interesting question there. Can we consider that to be an aggregation relationship where we have company as the whole and employee as the parts? How many people think we should do that? How many think we should not do that? Okay, the nots rule. And the reason is that, yes, it might very well be that the company goes bankrupt and all the employees have to be deleted. The people still exist, the employees have to be deleted. But you wouldn't really say, under any circumstances, that an employee is a part of a company in the sense of, they can, they belong to the company. Team members belong to the team. Think of the employees as roles of people, and think of the people as their fundamental entity there, the human. Okay, and they're not. I can see some logic where people would say, well, I'm a part of the team, and therefore I'm going to use the part-whole relationship. But don't use it when the real relationship is member that is joined and can leave, and that entity will normally go on and do other things, One of the things you're doing with aggregation and composition is conveying information to the designers that allows for certain kinds of design decisions to be made. And those design decisions relate to things we'll see on the next slide, so maybe things will become clearer when we get there. Any other questions? Yeah?
For the previous example, the vehicle stuff, if you destroy the vehicle's part will be destroyed too, so does that include in the composition too?
Okay, his question is should we call vehicle and vehicle part a composition? And I can see an argument for doing that. There's also a counter-argument which says that typically what happens before you send the vehicle to the wreckers is you strip the parts out, and parts can be taken out and put in other vehicles and things like that. Okay, that's the normal approach. Okay. One of the things we have to focus on is when we're doing this kind of analysis, we also have to think about what fundamentally is going to happen to the data. The data models the real world, but fundamentally, what we use in composition and aggregation for is to model what happens to the data. So in composition, we're saying that the data can actually be embedded, if we had a language like C++, in the parent object. And with vehicle parts, we probably wouldn't want to do that for the very reason that those parts can exist on their own and can be attached to other vehicles later on. Okay? We can show aggregations as a hierarchy if we want to. I don't very often see this kind of thing. And one of the things to be aware of, in fact, in this diagram on slide 28, is that we have all kinds of classes, frame, engine, transmission, wheel, that in fact might be examples of overdoing subclassing and having way too many types of classes that really we don't need. It might just be better to have a vehicle part class which has a description that says what it is, and a serial number and things like that, rather than have classes for every single possible part, because then every time I design a new vehicle that has new innovative types of parts, I've got to write new programming to program classes for those new types of parts, right? And I probably don't want to do that. So that's one of the reasons why we tend to find that aggregation hierarchies are extremely rare in practice. Maybe in analysis, one of the things I might want to point out to you is that in analysis time, you may very well have big hierarchies of stuff like this, and big hierarchies, big is-a hierarchies of animals and things like that, because you're trying to think about the real world. When you move into a real system, that's the time to collapse things down and say, okay, we're not going to have all those types of animals. We're going to use one class for animal type. We're going to use one class for vehicle part. We're going to use one class for music category rather than have a whole hierarchy. And don't get confused between the aggregation hierarchy and the is-a hierarchy. These are not inheriting from each other. You can't say a frame is a chassis is a vehicle. Okay, you say a frame is part of the chassis is part of the vehicle. Okay, so don't get confused. Two totally different kinds of hierarchies. Propagation is a concept that applies in the case of aggregations and compositions, where we want to say, okay, we're going to do something to the whole, like, for example, say, who is the owner of the car, and implicitly, that means that that is also the owner of the parts, for example. So that implicitly, that ownership association to the whole is considered to also apply to the parts. It's like an inheritance. But it's not inheritance because it's not automatic. With inheritance, if you have an association going into a superclass, that is automatically present in the subclasses. With propagation, if I have an association going into a whole class, that does not automatically apply to the part classes. I have to program it if I want it. So I have to then, maybe I have a method in the part class that says get owner. Well, it has to follow the link to the whole and then follow the link to the owner of the whole. Okay? It's not implicitly possessed, which is as is the case in inheritance. So it's not really inheritance. Very important difference. But nevertheless, we often do want to program propagation. Okay? Sometimes propagation can also propagate the other way. You can say, well, okay, the size of the parts when added together becomes the size of the whole, or the weight of the parts added together becomes the weight of the whole. So what is the weight of the whole? Go find the weight, add up the weights of each of my parts, and that is the weight of the whole. So I change the weight of a part, it has an effect on the weight of the whole. Okay? So that's also a kind of propagation, but it has to be programmed. So all propagation has to be explicitly coded, whereas inheritance is built into the programming language. Okay? And one of the reasons why we tag things with aggregation and with composition is to notify designers that there are probably opportunities for propagation here. Okay? But the designers have to code it up, program it, and so on. I've told you what interfaces are. Okay, an interface is like an abstract class, in the sense that it has abstract methods, except that it only has abstract methods. And it doesn't have any capability of having attributes, and at least not instance variable type attributes. It can have static ones. Can't have regular attributes. Can't have associations. Okay, it doesn't have data. It is basically just saying what methods are available. We diagram this in UML in one of two ways. On the left-hand side, you see I show a class-like box. I have a cashier label in that, and above that I have this thing, interface, in double angle brackets. These double angle brackets are called guillemets, and this is an example of what is called a UML stereotype. Okay, a stereotype is a way of tagging some special element in UML and giving it a more refined meaning. So we're using the class symbol, but we're saying, well, it's not quite a class, it's an interface, a special variant on the general concept of class. And then I'm showing my operations withdraw deposit. And I can show use my generalization triangle, but this generalization triangle now means implements. And I use a dotted line to connect that to the implementing classes to make it clearer that it's not actually a generalization. people can look and see it says interface, but they might not look there. And so the dotted line makes clear that it is, in fact, the implementation relationship, not the subclass relationship. The other way I can show these things in UML is to use these little lollipop symbols, as they're called. Little circle with a line, okay? And I just put the label cashier next to this little symbol to say this employee class implements cashier, so does ATM class. And the reason why these little lollipop symbols are often more convenient is because I may have many classes scattered all over the place that implement a given interface, and I don't want to have all kinds of lines crossing each other and so on. Okay, so this little notation is much more convenient and neat. But I can't show the operations. Okay, I'd have to show separately this box somewhere in the corner, and then have this little tag wherever I wanted to. Okay, any questions about that? You know the concept of interface, but this is how you diagram it in UML. Another thing we can have in UML is various kinds of pieces of descriptive text. In fact, descriptive text surrounding class diagrams is very important. You can put descriptive text in the diagram itself, and you can put the diagram in descriptive text. In fact, you should typically do both. So first of all, you're creating some kind of document. It may be a requirements document. It may even be a domain analysis document where you're showing relationships of things in the domain. And it may be a design document. In that document, you've got some text describing various things that you're requiring or designing, rationale and things that must be true, and you're using the diagram to illustrate aspects of the design. So the diagram is a figure in your document. Okay, that's the first thing. So a second thing is that we want to put little pieces of text called notes inside the document, describe bits of meaning that aren't clear from the document itself. Okay, so if something's not completely clear, add a note. And we'll see some notes in a few slides. One of the things you can do with notes is you can choose whether the notes are going to be just ordinary English in formal text, or whether they're going to be a more formal mathematical language. And in UML, the more formal mathematical language which we use is called OCL, Object Constraint Language. And we're going to spend a few minutes talking about OCL. OCL is used to annotate diagrams, all kinds of diagrams in UML. You'll see class diagrams here, but you can annotate the others as well. It can also be used standalone as text in your requirements document or your design document. In other words, separate from the diagram to describe logical things that are true about your requirements or your design. So it is a specification language. It is not a programming language. It is a language where all statements are basically just statements of truthhood. What things must be true. Okay? An expression specifies a fact, and your job as the designer is to make sure that when the system is implemented, all of these facts are actually true. It can't have any side effects. Okay? So you're constraining the design. You're not you're not computing values which are going to be assigned to variables or things like that. Okay, you're saying what is true. A side effect means something is computed and stores a value or returns a result which is then stored somewhere or has some side effect. I'm using a circular definition now. A side effect means that it has an effect other than just returning a value. Okay, and in this case, we always want to just return the true value, or false if the requirement is not adhered to. Okay, so true, it's a Boolean value that you're returning, nothing else, and mustn't compute anything other than returning the true value. In class diagrams, what we're going to do, we're going to see in a minute, is that they're going to specify what the values of attributes and associations must be. Things which we can't make totally clear from just looking at the diagram itself. in the statements that we write, which we'll see, you can refer to the names of things. So role names, association names, attributes, the results of operations. You can refer to those in your computations. The logical values true and false are part of the language. Logical operators, okay. String values, you can compare things to string values. Integers and real numbers and arithmetic operators, okay. All of these things can be part of expressions. But basically what you're going to be doing is you're going to be putting together the kind of expressions that you would typically put in an if statement. So if something, you know, or while loops, you know, those are the typical places where you've already in programming language been used to specifying logical statements. That's basically what OCL statements look like. You know? However, in C, you can actually, in C++, you can have side effects in your if statement. It's considered bad practice, but you can do it. In OCL, you can't. In OCL, strictly the result is the only thing that you're interested in. You're not allowed to have any side effects. Let's take a look at an example. Okay, that'll make everything clear. Well, maybe not, but hopefully. So in this example on slide 34, we have a hierarchy of shapes. This is not the same shape hierarchy we saw before, but it's another example of shape hierarchy. Linear shapes broken down into paths, lines, and polygons, and regular polygons. And a linear shape is composed of one or more line segments. We see the multiplicity, 1 to star, so one or more line segments. And a line segment is a segment of exactly one linear shape. Okay, so that's what we've seen so far from our understanding of UML class diagrams. We see the attributes start point and end point in line segment, which are points, and we see an operation length, which is an integer, phi, which returns an integer, and the path also has a length. Okay. Now let's take a look at some of these OCL statements. Underneath line, this is the simplest one, we see edge arrow size equals 1. This is written in curly brackets. When you see something written in curly brackets, you know it is a constraint, and we're using the OCL language to express constraints by default. So edge arrow size equals 1. What do we think about that? Well, how does this work? Edge is a reference to some name of something in the diagram. Okay? And where do we see the word edge in the diagram? We see the word edge over as a role name associated with line segment. Okay, so this is referring to the association to line segment. But it's referring to the line segment. So the line segment, okay, is what we're looking at. And arrow size means the number of line segments. Arrow is a built-in operator, right? Minus greater than. It's a built-in operator in OCL that says compute some value from the class diagram itself. So arrow size is a built-in operator in OCL that says the number of links of this edge association. So the number of links of this edge association must be equal to 1, is what we're saying. In other words, a linear shape has one line segment. Okay? So arrow size is built in. That you have to remember that. Okay? You can go and look at the book where I describe some of these things. You can also go and look at the OCL specification itself, which has a whole bunch of operators like this written up. Okay? The challenge for you: go to the OMG's website, find the OCL description among all the documentation. Go look up the built-in operators like size. Any questions about this one? Makes sense, right? A linear shape has one line segment. Okay. Because by default, it can have one or more. So in other words, this is basically saying that in this particular case, we're not allowing more than one, just only one. Let's take a look at another one that's slightly more complicated. Underneath path, we see length equals. Okay, so length equals is constraining the attribute length here of path. Equals edge dot length arrow sum. How do we pass that? Well, edge, as we know, is our representing our line segments, association to line segments. Dot length Okay, well, dot length is the length value, either attribute or operation. In this case, it's operation called length. So the edge dot length is the length operation of the line segment. Arrow sum. Okay, arrow sum is another built-in OCL operator that says add up these things. So adding up all of the edge lengths. Okay, if you add all the edge lengths, that must equal the length of myself, which is here. So the path length must be always equal to the sum of the lengths of the line segments that are edges. That's what this statement is saying. Okay? The concept is that this must be true when you implement the system. Always. And edge size must always be 1 in the case of line. That must be true. You're telling your designers to make the code so that is always true. Okay? Let's take a look at the one underneath polygon. Okay? Edge arrow first. Well, you see another one of these arrow things, another built-in OCL primitive. Okay? So arrow first means the first item in an association. So the first edge. And dot start point. Dot means go get an attribute or go get an operation. Dot start point in this case is an attribute. So the first edge's start point must be equal to the last edge's end point. First edge's start point must be equal to the last edge's end point. So in other words, you've got a bunch of edges that all connect up to each other and the first connects to the last. So we end up with a polygon, because if we didn't have this rule, we could just have a bunch of lines that kind of went, you know, like that. And this one here and this one here, well, they don't connect up, right? But they have to connect up, according to this. So that would be invalid. We'd have to make this thing come back down to there to make it valid. It still doesn't look like a polygon to me, but that's because we haven't got enough constraints. Any questions about that? Let's take a look at the one under regular polygon. Edge arrow for all. Anybody remember for all? For all in logic. There's a logical symbol that looks like this. You write it as an upside down A in logic. Well, because we're constrained to ASCII characters here, we show it like this. Basically, we're saying for all edges, okay? And then we have this whole thing in bracket. This is a more complicated piece of OCL. This is saying for all edges, take some values E1 and E2. In fact, take pairs of edges, E1 and E2. Okay, that's what it's saying. For all pairs of edges, E1 and E2, then the following statement must be true. Okay? For all pairs of edges, E1 and E2, following must be true. E1.length equals E2.length. So the length of a member of that pair must always equal the length of the other member of that pair. Okay? So for a regular polygon, that's a key rule, right? An equilateral triangle has all its edges. So you take any two pairs of those, they're going to be the same. So that is a way of specifying that in OCL. And the designers have to make that true. There may be plenty of other constraints you could also specify that would also make something clearly a regular polygon. But this is one of the things that must be true. Any questions? Okay. By the way, you might ask yourself, what do I expect you to know about OCL? Well, you could have a whole course in OCL. If I had my way, they would teach the Introduction to Logic course using OCL, because it is the language of software. It is the way logic is written in software engineering these days. And they would teach you the primitives and so on as they're built in. So that is, I'm just teaching you enough so that you get a flavor for it. I would expect you to be able to use these basic operators, but no more. Okay, so the operator size, the operator sum, the operator first and last, for all, okay, simple cases like this. But I'm not expecting you to do anything beyond the level of complexity of these examples. Notice up on between linear shape and line segment, we see open curly bracket, ordered, close curly bracket. Okay? That is a constraint in UML. It is one of the built-in constraints. It looks exactly like OCL, and for all intents and purposes is part of OCL. It is a built-in keyword that says that, in fact, the line segments are sequenced logically. There is a first, and there is a second, there is a third, there is a fourth, there is a fifth. If we don't put ordered on an association, we're saying we don't care about the order. In fact, the line segments will just be a random set of line segments that are in no particular order. Okay, so like the members of a club in an organization, we may not care about the order in which we store those members. We can, later on, we can sort them when we print them out for the user, alphabetical order or by order of membership number or whatever. But from the internal perspective, it doesn't matter. Whereas, fundamentally, the order of line segments in a linear shape does matter. Okay? We can't just sort of shuffle the order and still have it make sense. Okay? So that's why we are using this ordered constraint. Underneath line segment, start point, less than, greater than, end point. Less than, greater than is not equals in OCL. That's what it means. So what we're saying is the start point can't equal the end point. So that basically says it's not a point. It's not a single point. It is a line which actually has some length. It's not 0. We could have expressed this as length not equal to 0. Would have meant the same thing. Okay? And finally, above linear shape, we have this big behemoth of an OCL expression. And I think you probably should be able to figure out a good portion of this. Edge arrow for all E1, E2. All pairs of edges. For all pairs of edges. Okay? For all pairs of edges, everything below must be true. Okay. For all pairs of edges, the implies is a built-in piece of OCL. Okay? So for all pairs of edges, where E1 is not equal to E2, then the start point, E1 start point, must not equal E2's start point, and E1's endpoint must not equal E2's endpoint. Let's think about that a bit more. What are we actually trying to get at here? Okay? So we're trying to say, in effect, for all unequal pairs of edges, okay, for all distinct pairs of edges, these last two bits are true. So for all distinct pairs of edges, the start point of one must not equal the start point of another, and the end point of one must not equal the end point of another. So we can't have a situation where I have a pair of edges where I have start point of one also equaling the start point of another. So if you imagine the edge going this way and this way, okay, I can't have that start point. But the second part of that is saying at the same time, where's my eraser? At the same time, I can't have that endpoint on endpoint. So I can't have a situation where I have two edges that sit on top of each other. Okay? Basically, that's what that is saying. Because then you're not building up any kind of shape. You're building up just two lines sitting on top of each other. Yeah. Okay, a couple of minutes ago I explained what this piece of notation here. Edge arrow sign for all, E1, E2 is saying for all pairs of edges. Okay, for all is the logical operator, the upside down A, and E1 is an edge, where E1 is an edge and where E2 is an edge. Okay, so this is saying for all pairs of edges, for all any of the edges that exist. Okay, and in other words, any of the line segments that exist, because these are the edges. Okay, take any of those two pairs. Then compute the following. The following says where those segments are not the same. I mean, because if you take any pairs, in logic they could be the same edge. So E1 and E2 could be the same ones. So we're saying where they're not the same edge, okay, where it's not actually the same object, then we have this rule that says they can't sit on top of each other. Okay? I'm not going to explain that 3 times. I've explained it twice now. What I invite you to do is to go and read the book and puzzle the problem out yourself. and hopefully you'll be able to figure it out. Does anybody have any questions other than please explain it again? Yeah.
It seemed to me that the constraint for a polygon is not enough to make it a polygon, because you can have sort of an open polygon.
Okay. He's saying that the constraint for polygon is not enough because you could have an open polygon. Yes, it may very well be that there are not enough constraints here. What we're saying right now is that we can't have lines like this. We have an ordered set of edges. We definitely want somewhere to say that for each, if we have a sequence of lines, the first one, okay, looks like that. The end of the first one should be the same as the beginning of the second one, and the end of the second one should be the same as the beginning of the third one. Okay, if we add that down here, we do have a thing that says first start point is the same as end last point, so we know that we're going to have this. Okay, but that's still not enough because we could end up with exactly this. We could go like that, like that, like that, like that, and that doesn't define a polygon. So we'd have to have some other kind of rule that says that these things don't overlap. Okay, you're right. There would probably need to be several other constraints in here to make this thing proper. Those are left as exercises, okay? Any other questions about this? The purpose of this is to illustrate the existence and how these OCL expressions work. Here's an example of a class diagram. We're going to work through this class diagram over the next few minutes. A useful situation, a program for genealogy. Okay, we're modeling how people represent themselves and their ancestors and their cousins and relationships and marriages and things like that. Okay. So one of the things that we might do is we might just say, well, basically we're talking about people. So we have a class called person, which has name, sex, place of birth, date of birth, etc., etc., etc. Okay, a bunch of attributes. We have all these people in the system, and we have an association between people, child-parent. So basically a person has two parents, and a parent has some number of children, anywhere between 0 and... or a person has some number of children, anywhere between 0 and some arbitrary unspecified number. Obviously there are reasonable limits on that, but we don't want to constrain ourselves. And we also have the notion of, well, who was married to who? Okay, so somebody had 0 or 1 husband, and that person inversely had 0 or 1 wife. And by the way, the wife.sex must be female, and the husband.sex must be equal to male. Okay, all kinds of logical, reasonable things that seem to make reasonable sense to record family history. Okay, but there are some problems with this. First problem, it says a person must have 2 parents. Why is that a problem? Anybody figure out why it is a problem? Yeah.
You have divorce, but then again you have a child with...
Okay, well, you have a child with 2 parents. That is a biological fact. But why is it a problem to have it in the diagram here?
You might not know who the other parent is.
You might not know who the other parent is. It happens a lot. Okay? That's perfectly reasonable. But there's more than one reason. It's not just because when you were born, your mother didn't know who the father was. It also might be that you're looking back into the 12th century through ancient records, and the people at that time knew perfectly well who the parents were, but there's no records of it. Okay? Yeah?
In the person diagram, you also mentioned date of divorce and that aspect. So it might be that before the child is born, there might be a divorce. So when the child is born...
Yeah, right, okay. He's saying that, you've got date of divorce, and before the child is born, there might have been a divorce. That doesn't actually matter. There's actually another problem in here we're going to get to. And that's the second thing. It says marriage is not properly accounted for. Can somebody tell me why this diagram doesn't properly account for marriages? What is wrong with this diagram? Anybody tell me what's wrong with this diagram with that respect?
What if someone gets married twice?
What if somebody gets married twice? It happens. You know, your spouse dies, you marry again. And that happens in every culture.
many marriages.
Right. So, well, there could be polygamists too, and that happens in a number of cultures as well. So the point is that here we're just constraining one-to-one, you know, and for genealogical records, you've got to store all the information that might be logically true about family history, either your family or the family that you are doing the genealogical research for. Okay, so definitely we have to allow for more than one marriage for any given person. Okay, and it's irrespective of whether it's at the same time or not. I mean, the point is that people do have more than one marriage. Okay, there's also the question here of if we do have more than one marriage, then it's not clear here, you know, which, well, you know, things about like date of marriage, place of marriage. You know, there's only one place to store them, so we obviously got to move that out into a separate class. And that will solve some of the other problems we just talked about. Notice OCL constraints. Husband.sex equals male, male being a key value. We can show this as a string with little quote symbols. Here we're just showing it as a symbol, which means whether it's implemented as a string or implemented as a number or an enumerated type, we don't care. It is a distinct value that our program will manipulate, called male and called female. Maybe it's a class or something like that.
So it doesn't support same-sex marriages?
This doesn't support same-sex marriages, no. So in the current changing climate, there would also have to be changes there to handle that kind of thing. Parent for all P1, P2. Okay, for all pairs, we've seen this pattern before in OCL logic. For all pairs of parents, for all distinct pairs of parents, P1.sex must not equal P2.sex. So that means that irrespective of same-sex marriages, the parents of a kid must be of opposite sex. Okay? That's what this logical statement is saying. So you must implement your system so you can't accidentally enter data that would be inconsistent with that. You know, your system must constrain and prevent data that violates that from being allowed. Yeah?
But in this particular diagram, you're already constraining the husband to be male and the wife to be female. So it automatically implies...
Yes, it does automatically imply that, but it doesn't automatically imply that the parents of these two children are actually married to each other. Right? In this diagram. Anyway, later on, let's see some revisions of this thing, because this is going to fix up some of this stuff and make this a bit more clear. Okay. First of all, on slide 36, we split up the class. We've now got a person class and a union class. We're calling it union class to say, well, okay, you know, different cultures do things differently. Sometimes it's called marriage. Other cultures, people get together and there's nothing formal about it at all. And in other cultures, both things happen. So let's just forget about any. I've got attributes saying place of marriage, date of divorce, which allows for the formality to be stored in a union, but I can leave these blank if there's no formality there and there's no particular place, no particular date. I can always leave the attributes blank if I want. So we got these unions, and these unions are situations where basically two people got together for whatever reason, and they may or may not have children. A given union can have any number of children from 0 up to some arbitrary large number. And a child is a child of 0 or 1 unions. And the union is now called the parents. Parents in the plural, because a union is a pair. And we know the union is a pair because it says 0 to 2 partners. Well, why do we have the 0 dot dot by partner and the 0 dot dot by parents? Why do we have the 0 lower bound? Somebody tell me that. I've given you the answer several times. Speak up louder.
Child doesn't have to have parents.
Child has to have parents, but
One union.
we don't know necessarily who they are. We don't necessarily have the data. We might be looking at ancient records where we see a person and we don't know anything about the person, the parents. We might, for example, know, oh, okay, we have, you know, Thomas Matthias from 1492, you know, came across with Christopher Columbus to America, and there were records somewhere stored away that his parents were married, you know, in some place in Madrid, okay. So place of marriage of the union might be known, but we don't know who the parents were. We just have an annotation somewhere in his documentation that says his parents were married in Madrid. So we have this instance of this class. We do have one union with a place of marriage, but no partners. On the other hand, we might have information about the partners, but only one of them. Okay, or we might have both. Okay, so or we might have absolutely no information about a person's parents, in which case we'd have 0 unions associated with the parent association. Okay, so the point is that although logically everybody has 2 parents, and we don't necessarily know all the information, so we have to allow for 0 lower bounds because we can't store it. If you think about it, it would be impossible to store everybody's parents, because if we did, we'd have to store their parents and their parents and their parents and their parents all the way back to, depending on whether you believe in it, Adam and Eve, all the way back to the primitive unicellular organisms that were our ancestors a billion generations back. So obviously, at some point, we have to stop storing parents. You know, we just can't do it all the way back. Yeah.
In the first diagram, you have 2 parents. One is from 0 to 2, and the other one from 0 to 1.
Okay, that's an interesting point.
I still don't get that.
Okay, on the previous diagram, on the previous slide, so you're talking on this slide here, on slide 36. You're saying that we've got 0 to, okay, the union is the parents, okay? A pair. So I have 1 pair. I know it's a pair, but I don't necessarily know who they are, and the partners of the pair are these 2 people, and I may only know one of them or none of them. So this is the relationship of the partners of the union, and this is the relationship of you to the pair of people who were your parents. All right? And we see the same thing over on the right-hand side. On the right-hand side, however, I've made one change. I've said, okay, now I'm going to have a separate class, woman and man. And the reason why I might choose to do that is to allow for separate, so I don't have this complicated OCL expression that's on the far left. On the far left it says that the partner of one must not be equal to the partner of the other. Okay? Whereas over here what I'm saying is that, I'm just having 2 separate associations, union to female partner, union to male partner, 0 to 1. Okay? And there can be advantages to either. The advantages to the right-hand approach is that now basically one is the mother, one is the father association. They're labeled explicitly. Okay? And that can sometimes be useful in some circumstances. But the complication is that this requires 2 extra classes, which don't really have any separate information. I mean, there's no real separate encoding, no extra computation that goes on. There's only a different attribute. Nothing else would need to be stored there. So probably my left-hand implementation with a little constraint on this association. 1 association instead of 2, and 2 classes instead of 4. Question?
Don't both your solutions imply that the child has to come out of wedlock?
No, it doesn't. Because although I'm saying place of marriage, date of divorce, I'm not saying these have to be put in here. So you could just leave these out and say, okay, this is a situation where they weren't married. Okay, and then you don't even know whether they were married or not. Okay, which might well be the case. But if you did know, then you could put this information in. If your particular parents were married, okay, you could put this in. Right? These solutions are still not perfect. There are still some little glitches in this. There are the strange situations that can occur, for example, where what if, hey, your parents were married, you got divorced, and they got married again. Same people. Okay? Now, there's only 1 place to store place of marriage, date of divorce. Not 2. So maybe we can still work on this diagram further. So generally speaking, one of the things about UML diagrams is that there's all kinds of issues that come up that you have to think about. What are the ramifications? What are the little pros and cons of each one? Is one simpler than the other? Is one more complex than the other? Have we accounted for all the appropriate rules? Are all the appropriate OCL constraints in there to really say what we really mean by these things? Any more questions? Okay, next day, we've still got another 6 minutes. Next day, what we're going to do is we're going to spend most of the lecture on the board, actually doing problems. What I want to do for the next 6 minutes is just to tell you some of the steps that we're going to go through as we go about actually developing class diagrams. And then we're actually going to do that next day. We're going to go to the back of the book, pick one of the problems there, and work through it on the board. So how do you go about developing class diagrams? You know the syntax, you know the semantics, you know the kind of things that have to be there, but what's the procedure? Well, first of all, let's think about when you're going to create class diagrams. In domain analysis, you might create what are called exploratory domain models. These are models where you're just exploring the things that are true in the world. Later on, you might make a model that represents the same things that are in the domain model, the things in the world, but now a bit more constrained to represent the data that you're actually going to store. So in the real world, everybody has two parents, but in the data that you're storing, we don't necessarily know who they are. And so we refine our model a bit to take account of those situations about the reality of the data. And then finally, we have the system model, where we now add information about the software architecture. We add information about the user interface classes and other kinds of classes that are not actually modeling things in the real world. Most of the effort that we're going to go into in the next little bit will be into basically system domain models. That's what we're going to focus on. Okay, so the system domain model omits many classes needed to build a complete system. It omits user interface and architectural classes, and is often less than half of the classes of the entire system. And the complete system model is going to have all of these things, so user interface, architectural, and utility classes. And we'll see some of those when we get into the design stage later on. Slide 39 is telling you the sequence of activities that I suggest you follow when building a class diagram. First of all, identify a set of classes, candidate classes. Just brainstorm. Remember the brainstorming technique we talked about in Chapter 4. Brainstorm for a set of classes that will likely be in the problem. And you're going to do that by looking at the nouns in the problem description or in the rough requirements. Okay? Some of them will be classes, some of them won't be. But we're going to initially create a rough list. Then we're going to add associations and attributes. Okay? Starting with the classes that seem to be the most central and most important. Then we're going to start finding some generalizations, relationships, so we can push common attributes to the superclasses and common associations to superclasses. And then we're going to work on what we call responsibilities, which are abstractions of operations. Finally, operations. Okay, so we're going to follow this sequence. Right now we're going to work on the first three stages on the board, the classes, attributes, and generalizations. We're going to leave the responsibilities and operations till a bit later. And then you iterate. You iterate over this process. You iterate over it even while you're working on classes and attributes. You say you're working on figuring out some attributes and you discover a new class. Okay? Or you're working on generalizations and you discover new classes and then you discover new attributes. And so you're going round and round and round doing this until you feel it's right. Then you move on to the next stage, responsibilities and operations. You're also going to be doing things like identifying interfaces and working with design patterns. A key guideline is don't be too disorganized. We want to try and be systematic. At the same time, we don't want to be too rigid. We don't want to say, bang, got to do classes first. Bang, got to do associations and attributes next. Bang, got to do generalizations next. So if you first of all think of a generalization, hey, write it down. It's not a big deal. But try and be reasonably systematic and try and make sure that you've covered your classes to the best of your ability before you move too far down in this list. Okay? So, we'll leave it there today, and next day, basically, we're going to be working through this process of figuring out some example classes and doing a diagram.